Our goal is to examine standard probability distributions of random variables. In particular, we're going to examine aspects of the uniform distribution for computing probabilities related to a random variable that follows the uniform distribution. We're going to also examine the normal distribution, which is going to become a staple distribution in our exploration of inferential techniques in statistics. And then finally, we'll look at the binomial distribution. So to get started, let us consider first the uniform distribution, which will provide a natural segue into our discussion on the normal distribution. So we consider the normal distribution, but I would like us to first make a stop on the uniform distribution. Many of the underlying concepts and how we visualize probabilities can be illustrated by using a uniform distribution, where I'm going to show you how we can picture probabilities as areas. So imagine that you have a friend who is always late, and that means we're now interested in x, the number of or the fraction of minutes that has elapsed from when you're supposed to meet your friend until he or she shows up. So x is simply the fraction of minutes that this friend appears to be late. Now, sometimes this friend could be on time when you're scheduled to meet, in which case your x has the value 0 fraction of minutes, and sometimes the friend could be up to 30 minutes late. So this x, the number of minutes late, can go from at least 0 minutes if it shows up on time to at most 30 minutes if the friend really, really is late. And in this case, we notice that in this picture, our x on the horizontal axis goes between 0 and 30 minutes late. Now, there are fraction of minutes in between this 0 and 30, 1.5 minutes late, 2 minutes late, 7.3 minutes late, all kinds of fractions of numbers. And based on the definition and the realistic observation we've made, this friend can show up at any of these times. So what that means then is that each of these possible numbers are equally likely as the number of minutes that this friend can be late. Now, this horizontal lines I am drawing up is intended to represent in visual terms how likely each of these possible values could occur as the number of minutes late. Well, if they are all equally likely, that means they have almost uniform likelihood of occurrence. So we can say that x, the number of minutes late, which can have values between 0 and 30, has a uniform distribution because each of its possible values have a uniform likelihood of occurrence as being realized in a particular instance. So with this said, we can then ask, how high up are these bars or are these lines? How high up is it? Well, we know from previous work that if all of these lines represent likelihood of occurrence, then as a combination, they represent probabilities or probability. The sum of all probability, according to any probability model, must be equal to 1. So this provides us a basis to say that if we were to fuse all these lines together so that they make up an area, this would be an area that represents probability. And since probability adds up to 1, the sum of this area is 1. Then, how high up then is each of these bars? Well, I would say that 30 here, this span of 30 is being divided, is the number of times or the number of pieces into 1 is divided. So it means that each of these lines is almost as though they are sharing the total probability of 1 divided by this span of 30. So each of these lines must be 1 over 30 units high. I'm going to pull that picture here and see how we can use this to answer some questions based on the uniform distribution. For instance, if we're asked, what is the probability that your friend will be between 10 and 20 minutes late? Well, that will be the consolidation of all the lines, the uniformly high lines between 10 and 20. What that means is we would like to compute this area, which is definitely a fraction of 1. And what would that value be? So we're interested in probability that x, the number of minutes late, will be between 10 and 20 minutes late. Well, to do that, this looks like a rectangle. What is the area of a rectangle? The area of a rectangle in this case is length times width. Well, what is the length in this case? That will be how high up this line is. That will be 1 over 30. And then what is this width? That will be 20 minus 10, which is equal to 10. So my width will be 10. So this is 1 over 3. So there is a 1/3 chance that my friend will be between 10 and 20 minutes late. Okay? We yet want to look at another version of the problem. It is 10 a.m. That is the time when you and your friend are supposed to meet. And there is a 20% probability that your friend will arrive within the next how many minutes? In other words, in this problem, we have already assigned what? A probability, or the area of the amount of probability concentrated in this area. We only want to know how many minutes would it, from the time when you're supposed to meet, how long until that friend shows up, and that the chance that that will occur between 0 showing up on time and showing up at that unknown time is what? 20% probability, or 0.2. In other words, we are interested in how wide is this width such that this area is 0.2, or 20%. So we know already that area of a rectangle is length times width. The area in this case, we have been supplied the value of that area, that is 0.2. The length of this rectangle we know is fixed as 1 over 30, and the width is what we do not know. So in this case, to solve this, to isolate our w, I'll divide both sides by 1 over 30. So you have 0.2 divided by 1 over 30. And that would be equal to our W, will be equal to 6. So we anticipate that within what? 0 to 6 minutes that my friend will arrive. And that provides us with the solution we need here, which means that there's a 20% chance that our friend will arrive in the next 6 minutes. The takeaway from here is that we can use a uniform distribution provided you give the lower point and the uppermost point to compute probabilities. We can also use it to compute values that are unknown in the range of what? Possible values of x if we are provided with the probability. We're going to carry this idea of representing probabilities as areas into the normal distribution. What is the normal distribution model? Well, consider, for example, if we are looking at random variable x, which represents the heights of adult males in the United States. In my experience, 5 feet 10 inches, that'll be about 70 inches, thereabout. Let me convert that to inches, 70 inches. That seems to be the most popular height. So I am using this vertical bar and the the uprightness of that vertical bar to indicate how often we see this particular height of 70 inches in the population. it is the most popular. So there are other heights that are higher than 70 inches. Some people might be, let's say, 80 inches and thereabout. But talk about the basketballers. But they are not as many. So I'm not going to draw a line as high up as what I drew for 70 inches. And there are those who are not as tall as 70 inches. So I'm also not going to draw a bar that is as high as the one drawn for 70 inches. I'm going to draw a line to connect these points, and it looks somewhat like a floating ghost. We can say then that X, the height of adult males, since it has a particular value that is very, very common in the population of interest, and it has all other values that are spread away from it, which we measure using the standard deviation, of course. Well, that X is said to have what? A normal distribution model. Now, whenever we see a normal distribution model, let me sketch a little bit more of that. Let me bring a little bit of clarity here. So we have something that looks like this. So the number in the middle is the most popular number or value of that random variable. If it were the height x of adult males, that was what, 70 inches in the last example. In the example I just illustrated. And of course, there will be other values spread away from that typical height, either above or below. On average, we have to measure how far away are all other heights from the average height. And that is measured using the standard deviation. We're going to talk more about this in the next video.